Today we're going to do integration in other coordinate systems. I mentioned at the end last time that a lot of times the difficulties with these multiple integrals is that you do an integral of an integral. If the integrations you have get to be so hard, you can't find out what's the antiderivative of the function to be able to evaluate them. And the way you can solve that problem sometimes is by shifting to a different coordinate system where the functions to integrate are easier just because of the symmetry of the system. Really what we're interested in for all calculus books is just radial symmetry. What comes up in practice and the things people design like pistons and balls and all those kinds of things is sometimes instead of rectangular symmetry, you'll get a radial symmetry of some sort. In the plane, you might get a circle, right? And some other things you'd be surprised, like ellipses have a particularly simple description in the plane too that you can use polar coordinates for also. So when we have that radial symmetry, we're going to use polar coordinates, and that's the only alternative system we'll study in the plane. There are other coordinate systems. You can look them up online. It's kind of fun. There's parabolic coordinates and hyperbolic coordinates. There's a few things like that, but people hardly ever use them because what comes up in practice is circles or arcs of circles, sectors of circles, these kinds of things. And then sometimes integrating in polar coordinates can be much easier. In 3 dimensions, sometimes you'll get a spherical, a radial symmetry, right? Because gravity is radially symmetric. Maybe your integral of something in gravity is easier. Or designs of things. A lot of times they build spheres or things that are sort of sphere-like. You see those microwave antennas. They're not spheres. They've got kind of flat sides, but they go around a sphere. And so that's still easier in spherical coordinates. Cylindrical coordinates are also used. Sometimes you get cylinders for your pistons of your car or something, or cylinders for big vats that are holding fluid, and you want to integrate some fluid dynamics in there. So those are the coordinate systems that are of use. Is polar coordinates that you've already seen, and then cylindrical and spherical coordinates in 3 dimensions. All right, so here's the presentation then for polar coordinates. We'll first do the plane. Integrals in rectangular coordinates can be converted to polar coordinates. And then we'll do the 3-dimensional stuff probably next time. I don't think I have time to do much of it today. In polar coordinates, I just want you to recall, because you saw this earlier in the book, that they're like radar coordinates. Instead of dropping a perpendicular in the xy plane to the x-axis and saying, well, that's the x-coordinate, dropping a perpendicular to the y-axis, saying that's the y-coordinate and labeling it xy. Instead, you take the line segment from the origin out to the point you're interested in. Here's its coordinates, its rectangular coordinates xy. And if you take the line segment out there, the distance along that line segment you can call r, the radial distance we say from the origin to that point. And then the angle in standard position, counterclockwise from the positive x-axis, we call theta. And the ordered pair r theta also identifies a unique point, right? Each r theta you give me with r not negative in this context identifies one point. And sometimes that's a simpler way. I say radar coordinates because it's like radar, the radar sweeps around. Typically, radar sweeps clockwise for some reason. We're going to take positive angles counterclockwise. When you did these before, right, if r is the distance from the origin, then by the distance formula from 0, 0 to xy, r is equal to distance from the origin square root x squared plus y squared, right? And then also, if you drop the perpendicular here, so this is y and this is x, you recall from trigonometry that the tangent of this angle has to be y over x. That's the way it's usually defined in that XYR diagram, or in the unit circle. And so these are the equations we use to convert from rectangular coordinates, xy, also called Cartesian coordinates, to polar coordinates, r theta. Right? And Cartesian coordinates named also after Descartes, the famous philosopher. He was kind of an important guy, I think we mentioned before, for getting the mathematics ready to do calculus. And then Newton comes along and makes great strides with using coordinates. All right, so here's how you convert from rectangular to polar. You have to be careful, though, remember, because if you take a ratio y to x and say tangent theta equals that ratio, there's 2 different angles that can be. Right, this one and the opposite ray direction will have the same tangent, because if you put minus y and minus x, you'll have the same ratio and the same tangent, so you have to put it into the correct quadrant. You say tangent theta is y over x, and you notice this is in the second quadrant, so you take theta in the second quadrant in addition. Then if you go the other way, you drop this perpendicular and you have this right triangle here, and you notice this side length is our sine theta, this side is our cosine theta. And so you allowing for negatives, you say x equals r cosine theta, y equals r sine theta is how you convert from the polar back to the rectangular. I won't go through the whole argument on that because you've seen it before, but I'll just remind you, these are the two coordinate conversions you have to have memorized, so put stars by them, meaning rememorize them if you forgot them. Any questions on polar coordinates so far? You know, I really like this calculus book in general, but in this one section, I think they're lagging a little. One of the things they're lagging in is that in most textbooks, including trigonometry books, you have another description for polar coordinates. You can also let r be negative and theta be the opposite direction. So instead of taking this angle and going out this distance, r, the square root, right? The square root means the non-negative number that has that square, so it's a non-negative distance out. You can go around to the opposite direction, this direction, and make r negative, and the idea is that goes to the same point. You run at this angle and back up by minus this number. So you can let r be negative and theta be the opposite direction. That's also considered polar coordinates for the point. And then you can add 2k pi to either theta, and that's considered the same point. So there's an infinite number of ways to represent each point in polar coordinates by adding plus 2k pi to the r theta this way, and you can also take r negative in the opposite angle, and that's another description. So let's just say, to remind ourselves, convert these rectangular coordinates, minus 2 square root 3 for x, 2 for y, to polar coordinates. How do I do it? First one's easy. R is just the root sum square of it. Why do I take minus 2 square root 3 and square it, 2 square it, add them together and square root, and I get square root of 16 is 4. So this point here at minus 2 square root 3, 2 is exactly 4 units from the origin. R is 4, right? Then the tangent theta has to be y over x. Well, that's 2 over minus 2 square root 3. If I cancel the 2's, I can say it's minus 1 over square root 3. All right? How do I find theta? Well, you can say maybe it's the arc tangent, but you can run into the wrong quadrant that way, right? If I took the arc tangent of minus 1 over square root 3, it wouldn't tell me this angle. The arc tangent is between minus pi over 2 and pi over 2. It's first or fourth quadrant. So it would actually give me the wrong angle. What do I need to get if I use the arc tangent function on this? If I take arc tangent of minus 1 over square root 3, I'll get the angle over here in the opposite direction. I'll just add pi to it. So if you want to use the arc tangent on your calculator, say theta equals arc tangent of minus 1 over square root 3 plus pi. That way it'll get you to the right angle into the second quadrant. So first and fourth quadrants you use arc tangent. Second and third quadrants you use arc tangent plus pi. If you like, there's a computer programming thing. If you use MATLAB or C++ or any of those kind of things, you can say theta equals the a tan2 function of y first and then x. And in computer programming, just write that out. Bigger pen so you can see it online. So we'll just make this additional note. If you want the angle into the correct quadrant, you let theta be a tan 2. This does not tend to be in your calculators. Y comma x. And that command actually gets you the angle in the correct quadrant. It does that plus pi if you need it, basically. All right. And so, since I'm 4 units out, and arc tangent of this plus pi is let's see, minus pi over 6. Huh. Should have been 5 pi over 6 on this one. I wrote these backwards. Maybe not working. 4 and 5 pi over 6 to go over here. Sorry about that. And then this one will be minus pi over 6, the opposite direction. So taking it the way the book says it, you let r be the root sum square of these is 4 units out, and then tangent theta is minus 1 over square root of 3 quadrant 2 gives you arc tangent plus pi is this angle here, 5 pi over 6 on the unit circle. And 4, 5 pi over 6 is coordinates for this point. Now, if you let r be negative, then you can also take minus 4, but then you have to take the angle the opposite direction. Make this minus clear. It's minus pi over 6. All right. Any questions on polar coordinates? Does that look doable? All right, so with that in tow, then we can try and do integrals in polar coordinates. If the object here is to do the calculus with these things, that's to rehash polar coordinates. So suppose I look at this. Suppose I have that problem and I've got a nasty plane region, and I'm having trouble doing the integral because it's so hard, right? If you go from a min function to a min y to a max y or something like that, maybe those functions are nasty in rectangular coordinates, but if you put them in polar coordinates, they're easy curves. So I'm going to consider what we call radially simple polar regions. We'll take a region that's between a ray with angle and standard position, theta equals alpha, counterclockwise from the x-axis, and a rate of theta equals theta, constant value. So we're going to integrate from one ray to another, and then between an inside curve, r equals r1 of theta, and an outside curve, r equals r2 of theta. The idea being that r2 of theta is greater than or equal to r1 of theta. We then enclose this region R, and we don't want these rays to go all the way around in the region to start running over itself. So we restrict that theta can't be more than alpha plus 2 pi. You don't really run once around. When you do that, we can get these regions of this shape that we will call, when also r1 of theta and r2 of theta, right, writing r as a function of theta, are continuous curves, radially simple. Other books call them other things, like a simple polar region, so this isn't a set in stone term. But for a radially simple or simple polar region, we can deal with this kind of thing as follows. Here's a region here. You can kind of see it in the black. I wrote it in. If I want to integrate over this region, I can do like I did in the plane for integrating over non-rectangular regions of the plane. I'll just put a grid over it. In rectangular coordinates, we put a rectangular grid. In polar coordinates, we want to do something simple for polar coordinates. So I'm going to increment theta. Here's theta 0, theta equals alpha. Theta 1, right? Theta 2, theta 3, all the way up to theta n. We're going to increment theta from theta 0 through theta n. Then I'm also going to increment r. R is going to go from r0 to r1 to r2 to rm. We should call this capital N and capital M. And so we're going to increment r intervals, or m intervals in the r direction, n intervals in the theta direction. And we'll break this up into not a grid of rectangles, but a grid of what we call pieces of sectors, right? Each one of these little regions, like this one here, is you're taking a big sector on the outside. A sector is a slice of pizza like that. It's an arc of a circle on the outside and the inside. So arc of a circle on the outside and looks like that, a slice of pizza, 2 rays in here. So each of these pieces in here that I'm going to break this up into is a big sector minus a little sector. And I can find its area because we know a formula for the area of a sector, right? Here's the area of a sector from geometry, right? If you intercept through an angle theta and a radius r, a sector, then what's the area of that? It's actually 1/2 r squared theta. That's actually known just by taking the area of the circle is pi r squared, and then multiply it by theta over 2 pi, the fraction of the circle that you subtend with this angle. And so pi r squared times theta over 2 pi, the fraction of the area of the circle, gives you this formula for the area of a sector. With that in tow, I can now figure out how to integrate do a double integral of a function over this plane region here that's better in polar coordinates because it goes between two rays instead of being over a rectangle or something. All right, now this is hard to see over here. Maybe I should redraw this one. I don't know, but the idea is that, I guess I can't read it myself. You can't either. The idea is that in XYZ space, I can sketch this, and there's a simple polar region in the XY plane. It maybe goes between two rays here, between two rays, and it's like this, right? It's between two angles. There's my simple polar region. And then I've got a surface up over the top of this simple polar region, and maybe I want to find the volume below that surface. I'm trying to redraw this without messing it up, I hope. And this is Z equals f of XY as before. But it's over, that's the surface up here, but it's over a simple polar region instead of over a vertically simple or horizontally simple region in rectangular coordinates. How can I evaluate the volume below here with a double integral? Well, I'll do like before. I'll say double integral f of x, y, dA is defined to be, maybe I should write dEF just to remind us the definition. The limit is the number of rectangles goes to infinity, whereas the number of rectangles is n times n. Right, the number of increments in x times the number of increments in y. F of x k star y j star delta x k delta y k. This is the area delta a j k of the k little rectangle. When you did this in rectangular coordinates, how do I do this equivalently in polar coordinates now? I can take the limit as n goes to infinity. I can replace xk star with its conversion. Remember, x is r cosine theta, so I'll take rk star cosine theta k star, where I use these increments r and theta, the radial distance and the angle. R cosine theta will give me x, and rk star sine theta j star will give me y. I'll replace x and y with that. And delta ajk is no longer a rectangle, so it's not delta x delta y. I'm going to claim that actually this new thing, when you have these shaped regions, like this actually is the whole region here, a sector area minus a sector area, this comes out to be rk star delta theta j, put it in the other order, sorry, rk star delta rk delta theta j. Here you got delta xk delta yj because you were looking at little rectangular subregions, right? Base times or length times width. Here, however, you're looking at a piece of a sector of a circle. It's not length times width. It's actually equal to rk star delta rk delta theta j. That's what the jk area is when you're using polar coordinates and these shapes. And here's the reason why. Maybe I should redraw this one. Well, maybe it's all right. But here's why this little region up here has this area. You can hear it is drawn again a little bigger. Right? If I'm incrementing from rk minus 1 to rk, let's say, right? It's the kth subinterval. And I'm incrementing from this angle, theta k minus 1, to this angle here, theta k. So if the angle is delta theta k, I'm sorry, theta j and theta j minus 1, subscript. So this is delta theta j, the jth increment theta. I can find the area like this. Take the outside sector area minus the inside sector area. I'm going to put rk star half the distance between the two radii. So it's halfway between rk minus 1 and rk. And then we'll call delta rk the increment, the kth increment in r. And we'll say delta ajk, that is the area of this piece, the jk piece, is 1/2. Well, let's first do the outside sector. The outside sector, it's 1/2 radius squared times angle theta, right? It's 1/2 r squared theta when theta was the angle and r was the radius. This radius is now the middle point, rk star, plus 1/2 the increment, since this is halfway through. the radius at the middle plus half the distance across. So that's the radius squared, and delta theta j is now the angle instead of, I used to call it theta, I'll now call it delta theta. So 1/2 r squared theta, where the angle is at, we'll now call delta theta j, and the radius is measured this way, rk star plus 1/2 delta rk. So that's the area of the outside sector. Now I also have to subtract off the area of the inside sector, which is 1/2 r squared theta, with the same angle, delta theta j, but now I take rk star and subtract half the increment, delta rk. Right? By the way, this proof I didn't see in your book. I said this is where I think the book is lagging. One, they don't derive this to show you why it works. Maybe I just missed it. Maybe it's somewhere else. And the other thing is that they don't show you negative r in polar coordinates, which are very popular. By the way, this formula going to works in when r is negative also. You just have to be careful to use it correctly. But anyway, you have then, this is the outside sector area minus the inside sector area. And then you multiply this all out and you say, well, by foiling, this is rk star squared plus 1/2 rk star delta rk plus the same gives rk star delta rk. Plus this one squared is 1/4 delta rk squared. So this is the square of this one. That multiplies delta theta j and 1/2. All right, so I'll put those here. And then this one squared gives rk star squared minus rk star delta rk, right? So this times this is 1/2 that, and you get it twice in foiling. And then plus this one squared is 1/4 rk star squared. Well, when you subtract those, right, outside area minus inside sector area, these four cancel, right? This one cancels this one cancels this one. If you don't follow every step, that's okay. I'm not going to ask you to recreate this. I just thought it was worth seeing, so you don't always scratch your head in industry and say, why does that work, right? The reason you have to do this is these aren't rectangles. You can't take length times width. But when you subtract these out, you have these two terms left. This one minus the same, they're both the same. All times 1/2 gives one of these, which is just rk star rk, delta rk, and then all times delta theta j at the end. So here is the area we just proved in terms of rk star, the point halfway out, the increment delta theta j, and the increment delta rk for the jk piece. All right? That's what we need to call delta a jk using this shape piece. Now we said to evaluate this thing, recall on the other page, what we're going to do is take the limit of the sum, f in polar coordinates, times the area of the cake piece, rk star delta rk delta theta j. That's what we just proved. And so now we can say, here's the formulation when you want to do a double integral polar coordinates, right? Its definition is the limit of that double sum. And what you can prove is that for a simple polar region, meaning that R1 of theta and R2 of theta, the inside and outside curves of the original region, here it is again, the inside curve and the outside curve are continuous, and you're between two rays. That's a radially simple or simple polar region. For those kinds of regions where the function you're integrating is also continuous, so basically, again, it's just everything's continuous. And then you can do piecewise continuous, it turns out to work too. This double integral defined to be the limit of the sum f in polar coordinates times delta ajk in polar coordinates is actually equal to the limit of the sum in rectangular coordinates. The differences you can prove go to 0. So to evaluate the double integral in polar coordinates, I can do this limit of the sum with polar areas. Well, what is this in calculus from what we did for limits of sums? According to our definition of the iterated integral, this is actually equal to the double integral, can be written as, by their theorem, I guess I should say, for iterated integrals, as the iterated integral from minimum theta to maximum theta, lower curve R1 of theta, upper curve R2 of theta, f written as a function of R theta, and then the rk star delta rk delta theta j becomes r d r d theta. That's our theorem, is that you can rewrite it like that. So what we've established, but I had to wave my hand over to avoid the details, is this theorem. For a function, for an integram that's continuous on a radially simple region, in what we showed, the double integral over the region can be evaluated by an iterated integral. F replace x and y with r cosine theta or sine theta. dA replace with r dr d theta, not dr d theta because it's not a rectangle, it's a piece of a sector of a circle. All right. Any questions on all that? That's all the theory. The rest of the time I want to do examples. The theorem, put it off the top a little there. And look okay. But the idea is to just be able to integrate polar coordinates because it'll make a lot of our integrals easier. This one is not going to be easier. This one is about equally easy in rectangular or polar coordinates, but this will illustrate nicely how to use polar coordinates in a non-trivial case. Suppose I wanted to take the double integral of y dA, so we write it this way, defined as the limit of the double sum, right, of y, over this region that's a triangle. As you might guess, you can do this in rectangular coordinates. Triangles aren't too hard in rectangular coordinates. What if we wanted to do it in polar coordinates? We actually can because this is also a simple polar region, right? It goes between an angle here, a ray here, I should say, and a ray here, and it has this inside curve, r equals 0, the origin. By the way, in polar coordinates, we call it the pole usually instead of the origin. And an outside curve here, x equals 2. So I go from inside curve r equals 0 to outside curve r equals 2, not r equals 2, x equals 2, both continuous. And between two angles here, theta, if the line theta equals x and the line y equals x and the line y equals square root 3x. Sometimes I have to slow down. Slow me down if I start to misspeak there. All right, so that makes sense. I can also call it a radially simple region because it goes between two angles, and an inside curve and an outside curve. The trick is you have to rewrite those all in polar coordinates, right? And that's a little bit of a challenge. But what we can do is this. We'll say, what angle is this? I find the intersection point here, right? I say I'm intersecting the line y equals x with the line x equals 2. So I just put 2 into here and get y equals 2 at the point 2, 2 right there. The ray goes through the point 2, 2. We infer, oh, that's a 45-degree angle, right? Because it's y equals x here. So this is a pi over 4 angle to this ray. Then how about this one that goes through 2 square root 3, 2? I'm sorry, 2, comma, 2 square root 3. I wrote those in backwards, the standard order. I know this one because I know x equals 2 here, right? And I put in 2, I get y equals square root 3 times 2. So there's the coordinates of that point, and I can figure out what angle it is by saying tangent theta in polar coordinates is y over x, 2 square root 3 over 2. Stop me if there's any questions. Does that make sense? Tangent theta equals y over x in polar coordinates. We can cancel the 2's and say that's square root 3. I wonder what angle that is. When you can find it exactly, I want you to find it exactly. You could use the arctangent square root 3 function on your calculator, and some calculators will give you an exact answer. It's pi over 3. But if you haven't got such a calculator, or if I give you something that's, in another quadrant, so you're supposed to add pi, you have to figure that out. It's better to do this on the unit circle. So I'll rewrite square root 3 as square root 3 over 2 over a half, because I recall from trigonometry, that's a point on the unit circle. Here it is. If y is square root 3 over 2 and x is a half, right, then I've got this little triangle here, which is the standard one for trigonometry, side 1/2, side square root 3 over 2, and side 1. It's a 30, 60, 90 triangle. This must be a 60-degree angle, pi over 3. So I figured out that this is pi over 4 to here, and this is pi over 3 to here. Those are the two rays, angles of the two rays. Now I just need inside curve and outside curve. The inside one is easy. The pole has equation r equals 0, right? This one out here, we said the equation x equals 2. I have to convert it to polar coordinates. So x is r cosine theta, so r cosine theta equals 2 is polar coordinates equation for this. But, right, in the formulation here, I have to write r as a function of theta for the inside and outside curve. So I have that here, r equals 0. On the outside curve, I need to write r in terms of theta. By the way, we won't in this class ever write theta as a function of r. In all applications I see, r is always a function of theta is how you write curves. You saw that already in the polar coordinate section. And that's what happens here. We'll always, in polar coordinates, integrate with respect to theta on the outside between two constants, two numbers, where the top number is never more than 2 pi plus the bottom unless you overlap your region. And the inside ones will go between two functions that could depend on theta, or they could be constants, depending on the region, right? Here, the bottom one, r equals 0, is a constant, but the top one, this line, x equals 2, is also r cosine theta equals 2. And you divide by cosine theta, you've got r equals 2 over cosine theta, or 2 secant theta. There's r written as a function of theta, and that tells me how to rewrite this integral. It has to go from min angle to max angle, two numbers. Min inside curve r is a function of theta, to max outside curve r is a function of theta. So I'm going to go from pi over 4 to pi over 3 with two angles. Inside curve r equals 0, so I put 0. Outside curve r equals 2 secant theta, I put 2 secant theta, a function of that endpoint, just like we did in rectangular coordinates. So there's the integral, and now I replace the integrand y with its polar coordinate equivalent r sine theta, so I put an arrow down here. And when I replace dA, I don't put dr d theta. What do I put for dA? See if it puts you to sleep or not. Right, we said we put r dr d theta. Right, that was what we derived there. The little area increment delta aj is rk star delta rk delta theta j. And so when you write that in integral notation, it's r dr d theta. All right, so replace dA with r dr d theta, replace y with r sine theta, min theta to max theta, inside r is a function of theta, outside r is a function of theta. That's how you set up a polar integral. Well, how can I do this? Here's the tricks that are often useful in the book. I'll take r times r and call it r squared. This sine theta on the inside integral with respect to r this is a partial integral again. And so you can pull the sine theta out of there and put it still inside this integral. You can't ever take the theta out of the theta integral, but you could, and so the r squared has to stay in the inside integral because I'm integrating with respect to r. I can't pull an r squared out of the r integral. But I can pull the theta out of the integral, sine theta out, because it's treated as a constant in this integral. So I do that. I pull sine theta out here. I'm left to integrate r squared from 0 to secant theta. And in some of these problems, you can then take this inside integral and say, oh, it's a constant, and pull it out to the outside. Can I do that here? I can't. I can't pull this one out and write it as the product of integrals of this one, because this integral, when I evaluate the top endpoint, becomes a function of theta. I can't pull a function of theta out of the theta integral. So I'm going to have to leave this in here in this case. If it goes between constants, you can pull it out because the integral is a constant, but this one doesn't. So I'll evaluate it within this other integral. And here's what I get. Integral of r squared is r cubed over 3. That has to be evaluated at 2 secant theta and theta and take the difference. Right? Now that means the top endpoint, you get secant cubed over 3. 2 secant quantity cubed over 3 is 8 secant cubed over 3. Plug in 0 at the bottom endpoint, that's 0. So you just, the inside integral just evaluates this way, 8/3 secant cubed. Now I've got a calculus 1 integral, sine theta times 8/3 secant cubed theta from pi over 4 to pi over 3. I just go back to calculus 1 or calculus 2 maybe for the technique and try and figure out how to evaluate that integral. All right? How do I evaluate this integral? Well, maybe one of the things you remember, and this is one of the things I want you to pick up out of this course, is become very good at integration. Right? In calculus 1, you got very good at algebra because you used it all the time. This course, we're going to use integrals all the time, and you're going to remind yourselves of your techniques. You'll be good at integration, hopefully, you get out. That's one of my goals. All right? Remember, if you have a power of sine times a power of cosine, there's a technique for doing that. If the one power is odd, you let u be the other power. Like if you have sine to an odd power and cosine to an even power, you let, since the power of sine is odd, you'll let u equal cosine theta. If the power of cosine is odd, you'll let u equal sine theta. We can do that here, right? Even though it's a negative power, we can still do it. To integrate sine theta over cosine cubed. I'll first write it that way, remembering that I can do powers of sine times power of cosine with a substitution. And I'll let, since sine is to an odd power, I'll let u equal cosine. In that case, right, if I let u equal cosine, then du has to be du d theta d theta. The derivative of u d theta is minus sine theta d theta. Well, if du is minus sine theta d theta, put that in here. Then this all gets replaced by minus du, right? This is just minus du. Cosine cubed gets replaced by u cubed. And then I have to change the endpoints to what u runs over, right? Remember that? So I'm going to integrate, replacing this with minus du. The minus comes out and I put du. This 1 over cosine cubed is 1 over u cubed. And look at what an easier integral that is. Now I just have to integrate u to the minus 3. Easy one. And the endpoint switch, right, when you're at the bottom point, pi over 4, for theta, u is cosine pi over 4 is square root 2 over 2. You change that to square root 2 over 2. When theta is the top endpoint, pi over 3, u is cosine pi over 3 is 1/2. So you change the top endpoint to 1/2. So you put in the u limits now in this integral, or you can put on here theta equals pi over 4, theta equals pi over 3. If you're going to convert it back in theta and then plug those in, you can do that too. All right. Well, I'm going to then evaluate integral of u to the minus 2 of minus 3 is u to the minus 2 over minus 2. Overwrite it that way. All right. That's the antiderivative. We're just doing calculus 1 at this point. And it goes between 1/2 at the top and square root 2 over 2 at the bottom. And it's all multiplied by minus 8/3, right? That means there's a question. Then I think it's simpler if you rewrite square root 2 over 2 as 1 over square root 2, right? They're equal. This one just isn't rationalized. So I'll write that way. And now I realize I've got, let's see, 8 minus 8 over 2. Minus is canceled. 8 over 2 is 4. 1 over 3. I've got 4/3. 4 over 3 u squared. This simplified algebraically. I have to plug in 1/2 at the top and 1 over square root 2 at the bottom. All right. And so I plug in the 1/2. I got 4 over 3/4. I plug in the bottom. U squared is 1/2, so I get 4 over 3/2, and it's just fractions at that point, right? This is 16/3 minus 8/3, it gives me 8/3. The value of that integral is actually 8/3, and if I thought of this geometrically as a volume, what I'm saying then is that, let's go put the picture back. If I took the volume of the solid that's of height y over this triangular region in the xy plane, its volume would be 8/3, right? So you put the plane z equals y up over this triangle and make a solid, and that solid would have volume 8/3. Is geometrically what that means. Although, as we said last time, there are other applications than finding volume integrals, things like finding mass from density or enclosed charge from charge density. And there's some other ones coming up, moments of mass and those kinds of things. This is the application section that's coming up after we finish this one, actually. Now, here's a second example. Suppose instead I want to do, this will be an easier one. Oops, there we go. This one. Put the wrong page. This is where a problem that screams for polar coordinates. When you get out of here and work in whatever scientific capacity or something, if you see a region here that's a half disk, right, instantly think polar coordinates, because this has a nasty equation of rectangular coordinates, right? X squared plus y squared equals 16. If you write y as a function of x, it's y equals square root 16 minus x squared. That's going to be ugly to integrate, square root 16 minus x squared. You don't want to do that, right? That's the curve in rectangular coordinates. But if you put it into polar coordinates, this arc of a circle here just has equation r equals 4, a constant. What's easier than variable equal a constant, right? That's if you drew r theta axis, it'd be a rectangle, right? But theta goes between this ray, theta equals 0, this ray, theta equals pi, and r goes between an inside radius of 0 and outside radius r equals 4. Thinking of this as a simple polar region, right? We're thinking it's between theta equals alpha and theta equals beta. Inside curve r1 of theta, r equals r1 of theta. Outside curve is the region, r equals r2 of theta. That's what this is, right? The outside curve is r equals 4, the inside is the point, r equals 0. The rays are theta equals 0 and theta equals pi. Part of the problem is just figuring that out. But look how simple it is. Theta goes between two constants, r goes between two constants. It's a rectangle in our theta space, right? And so we're going min theta to max theta, inside curve to outside curve, and now all the endpoints are constant. This is a huge advantage, right? You can do this one easily. And my integrand, square root x squared plus y squared, is also screaming for polar coordinates because that's just r, right? R is square root x squared plus y squared for polar coordinates by our transformation equation. So we just have to integrate r between these endpoints. Now we also replace the a, not with dr d theta, but with r dr d theta, a little area element. And now we realize we made such a simple problem out of this that the inside integral is actually a constant, right? Since we're integrating r squared from 0 to 4. When we plug in these and take the difference, this will just be a number, right? Since it's constant in points. Since this is a number, we can pull it out of the integral and rewrite this integral of an integral with this one outside as a product of integrals. We just have pull it out and we get integral d theta times integral r squared dr from 0 to 4. Integral d theta means 1 d theta. There's a 1 assumed in there. Right? And so integral of 1 is theta. I plug in pi and 0 and take the difference. Then integral r squared is r cubed over 3. I plug in 4 and 0 and take the difference. Look how easy that is in polar coordinates. We would have been all day doing it if we can't get a coordinate. But right, 4 cubed over 3 minus 0 cubed over 3. All times, this one is just pi minus 0 pi. Gives us 64 pi over 3 is the value of this double integral. Whether it's a volume or a mass or whatever it is we're calculating, there is the evaluation of this one. I guess I could have kept that on the screen, the whole thing. Yeah.
I'm still a little confused on how you find the limits for polar coordinates. Can you go over that?
Yeah, what you do is you think of this picture here, that r goes between one ray, theta equals alpha, and another ray, theta equals beta. And so I'm thinking, I can sweep this region out by starting at this ray, sweeping it all the way around to the other ray, and make this the inside curve and this the outside curve following this diagram. The inside curve r is a function of theta, and outside curve r is a function of theta. To get a region of this form, you just have to think of beginning constant ray and an ending constant ray, just a straight line from the origin. Outside curve r is a function of theta, inside curve function of theta. That's how you do it. And so you say the inside curve is a point, it's just the origin, so it's r equals 0. The outside curve is a circle with equation r equals 4, doesn't even depend on theta, it's constant. And this is the beginning ray and this is the ending ray. Swept out this way, r goes from 0, theta goes from 0 to pi. But I don't do any more of that. I think of this picture every time and try and figure what's the minimum ray, what's the maximum ray, what's the inside curve, and what's the outside curve. The radially simple region. All right, it's Friday. Go have a nice weekend. Not very many people are coming to my office hours. Please feel free to get on. I've got the web thing on the. I've got the web address on my syllabus. Just look that up anytime and come see me.